A random forest grows many trees in parallel and averages their independent guesses. Gradient boosting flips that idea completely on its head. It grows trees one at a time in sequence, and each new tree has just one job: to fix the mistakes that all the previous trees left behind. Done well, it's often the single most accurate model you can train on everyday tabular data. Let's start as simply as possible. We make one rough first prediction for a regression problem that might just be the average of all the target values. A flat, boring guess. It's wrong almost everywhere, and that is completely fine. The whole point is just to have something to improve on. Then, for every single data point, we compute the residual, the gap between the true value and our current prediction. Taken together, these residuals are a map of our errors. Here we guessed too high, there we guessed too low. Now comes the clever move. We train a small tree, but not to predict the target. We train it to predict those residuals. In other words, a little tree whose entire purpose is to learn the mistakes we just made. We add that correction tree onto our running prediction, but only a small fraction of it, scaled down by something called the learning rate. A gentle nudge in the right direction, never a wild leap. Then we recompute the residuals, and sure enough, they've shrunk a little. And then we just repeat. Another tree on the new smaller residuals, another gentle nudge, the errors shrinking a little more each round. Hundreds of tiny trees, each one quietly cleaning up after the last, slowly sculpting a remarkably accurate model. That's gradient boosting, and it's really gradient descent, except each step is a tree. Now the trade-off: more trees and a higher learning rate fit the data harder, but push too far and you'll overfit. So the learning rate and the number of trees are the two dials you balance against each other. As a rule of thumb, slow and many tends to beat fast and few. In Scikit-Learn, it's gradient boosting classifier. You set n estimators and the learning rate, and then it's the same familiar fit, predict, and accuracy score. And by the way, the famous libraries XGBoost and LightGBM are just turbocharged versions of this very same idea. Let's write it. Here's the program, one page, every line visible. The shape is identical to the forest from last time. We're really only changing which model we build. Let's read it. The imports: make classification for the data, and this time gradient boosting classifier from sklearn.ensemble plus the usual split and accuracy score. We build a dataset, 800 rows, 20 features, only a handful of them informative. Boosting tends to really shine on richer data like this. Split it 80-20 with a fixed random state. Same as always, nothing new. Here's the model. Gradient boosting classifier with n estimators of 200, a learning rate of 0.1, and shallow trees of max depth 2. Those small trees are the gentle correctors. Then we fit, and it builds the 200 trees one after another, each fixing the last one's errors. Predict and score, typically very high, around 92% here. Each tree only nudged things, but 200 nudges add up to a sharp, accurate model. And for the figure, a lovely one. We use staged predict to grab the model's accuracy after every tree is added, and we plot it. You can literally watch the accuracy climb tree by tree as the boosting does its work. And that's gradient boosting, sequential trees, each correcting the last, nudged gently by the learning rate into one very strong model. It's the quiet workhorse behind countless winning solutions. Next time, something totally different and refreshingly fast, naive Bayes built on pure probability.